plane Euclidean geometry we have defined the area of some simple plane figures. The area of a triangle is half the product of a side times the corresponding height. The area of a rectangle is the product of two adjacent sides. The area of a circle is pi times the square of its radius, where pi is equal to 3.14 approximately. The area of an ellipse is pi times the product of its two semi-axes. The areas of some more complicated plane figures can be calculated from these areas, if a figure is composed from instances of the previous figures. But what is the area of an arbitrary plane figure? In elementary geometry we do not have a general definition of the area of a plane figure. Therefore, we need a general definition, which will also give a method of calculation of the area. This objective, for a large class of plane figures, is achieved with the Riemann integral. Let us start with a simple plane figure A and try to define and find its area. Drawing some horizontal and vertical straight lines, we can split this figure into smaller plane figures. Each of these smaller figures has the following property: its border consists of one or more straight segments and at most one curved segment. Therefore, we want to establish a procedure that will define and find the area of a plane figure that has three, at most, straight sides and one curved side. Choosing a coordinate system with axes parallel to the two sides of this figure, we obtain the essential problem: define and find the green area of the figure. After finding all the areas of the smaller figures, we can add them and have the area of the original figure A. We restate now the essential problem precisely. In a two-dimensional Euclidean plane we have a coordinate system with axes OX and OY and the graph of a function f of x in the closed interval AB, or larger. We draw the normal lines to the x-axis at A and B. We want to define and find the area of the figure with borders the x-axis from below, the two vertical lines at A and B from left and right, and the graph of the function f of x from above. Our first step for solving this problem is to choose an ordered set of points x0, x1, x2, etc. up to xn, as in the figure. This set is called a partition P of the closed interval j equals a, b. This partition divides the interval j into n intervals jk with length dk. The maximum of dk is the norm d of the partition. We choose now a point tk in each interval jk. Thus we have the two sets p and t. It is emphasized that all the points xk and tk are otherwise arbitrary. In the second step we consider the rectangle with base the length dk and height f of tk. Its area is dk times tk. Adding up the areas of all such rectangles we obtain the sum S, that depends on f, p, and t. This is the Riemann sum. The Riemann sum depends on the points xk, tk, and the function f, whose graph is the upper side of the figure. We give now the following definition. If there is a number I, such that for every given positive epsilon there is a positive delta, such that for any p, t with d less than delta, the absolute difference s minus I is less than epsilon, then I is the Riemann integral of f from a to b. From this definition is clear that, if a smaller epsilon is given, probably a smaller delta must be chosen for the absolute difference s minus I to be less than epsilon. This means smaller dk and more rectangles. In the figure this will bring the tops of the rectangles closer and closer to the graph of f of x. This is a limiting procedure in which the upper sides of the rectangles tend to approach the curved upper side of the figure. But it is not a limit, because the Riemann sum depends on many parameters, not one as for a limit. For this reason we define the area of the figure as equal to the Riemann integral. We have reached our objective to define the area of many general plane figures. The Riemann integral I is denoted with an elongated capital letter S, to remind its origin from the Riemann sum. The data involved include some important new concepts, the function f is the integrand that needs to be integrated. If the integral I exists, the function f is called Riemann integrable on a, b. The interval a, b is the range of integration or interval of integration with lower limit a and upper limit b. The previous definition of the Riemann integral opens a whole field in mathematics, with theory, applications, and problems. Some of its first consequences follow. 1. The existence of the Riemann integral depends on the behavior of the function in the range of integration. For example, if f of x equals 0 for rational x and f of x equals 1 for irrational x, it is easy to prove that the Riemann integral from 0 to 1 does not exist. 2. If the Riemann integral of a function on a, b exists, it is unique. A proof by contradiction is possible. 3. If the Riemann integral of a function on a, b exists, then the function is bounded on a, b. If we assume that the function is not bounded, we can show that the Riemann sum can exceed any number. 4. A continuous function, a step function or a monotone function is Riemann integrable. This proof is not so simple. 5. A part of the graph above the x-axis contributes positively to the Riemann integral. A part of the graph below the x-axis contributes negatively to the Riemann integral. This is obvious, because the factor f of tk in the Riemann sum has the sign of f of x. Detailed proofs of all these statements, more properties, and extensions to other integrals can be found in Calculus of One Variable by S. Persidis.